to the Rochester chapter IS&T November meeting. Thank you all for coming. We want to give a special thanks to RIT for hosting this here on site. Thank you, Karen, for allowing us to be here. Okay, so with that, I'd like to introduce our speakers for tonight. It has now been officially 25 years since the publication of JPEG 2000. It was, what, this month or next month when it officially came out? 25 years ago. So we are very honored to have three of the people on the committee right here living in Rochester. When it came to imaging science, imaging compression, the world came to Rochester to find the experts. I won't go into their bios, but we have more than a century of experience behind these three speakers, combined total experience. So, Bernie, are you going to be kick it off? So with that, I will turn it over to Bernie. Thank you very much. Looking forward.
So just background from me, I grew up in Rochester, went to RIT, never left the area code, but a few times growing up and started with the JPEG committee and started kind of internationally all over the place and making decisions on things that were waiting on my feet. So it was one of the great experiences of my life trying to deal with other countries and the politics as well as what's important to different countries and things like that. So let's go with some. We're going to talk. So we're going to go through some background of JPEG 2000. I want to talk how it started. Majid will get into some of the details of what it was, and then we'll all come back and we'll talk about follow-up format, and then we'll talk about some successes. Okay, so introduction to JPEG 2000. So the kind of what was the pushing, driving of JPEG 2000 were kind of three markets. Geospatial market, that's remote sensing, that type of stuff. That's what I was doing. Medical markets, that is, all of a sudden we were getting MRIs and CAT scans and all these digital things that were multi-band and multi-resolutions and a lot of bigger, right, and greater bit, as well as scanning of document, right? So those three things were really the pushing of JPEG 2000 because the JPEG original DCT wasn't meeting these markets, right? JPEG DCT was great and it technically is the most successful ISO standard of all time, but it was not meeting these markets, right? And in digital cameras back in '94 weren't really around. I mean, the state of the art then was Apple QuickTake 100, which is a quarter megapixel for consumer, and then the DC 460 or something like that, which is a couple megapixels for professional, was 13,000, right? So at the time, these markets were really pushing for the requirements of JPEG. Okay, so the real start of this, we were working on the original JPEG had a lossless mode, wasn't very good. So we started a new work item called JPEG LS, a lossless version. That was being tested and evaluated with a bunch of people submitted ideas. Rico put forward a waveless, a lossless waveless compression called True. They kind of were in the market for digital cameras as well as medical and other things. And so they put that forward. It didn't win JPEG LS, but it was Martin Woliak was the kind of pushed this forward as, hey, we want to start something new, a wavelet, lossless wavelet compression as a new work item. I was working with Aware and Arizona, University of Arizona, Dr. Marsland, and developing a wavelet CCQ algorithm for geospatial applications. So me and Marty got together and we said, okay, let's really push this. And so we pushed to start a new work item that's focused on better compression. And of course, the engineers think that they're marketing people, so we made the JPEG 2000, bringing compression into the next millennial, right? Horrible idea, since that meant we had to really get it done by 2000, right? So there was the main requirement, superior performance in low bit, right? Back then, hard drives were still really expensive. So having terabytes of data, getting 10% or 20% improvement was a significant amount of money, all right? As well as bandwidth was not very big, right? Progressive transmission by pixel X-ray accuracy and resolution. What you saw is a bunch of things that were being wrapped around JPEG, like flash pics and some other formats, as well as some competitive wavelet algorithms that were out there that were trying to meet those needs in the commercial market. So, you know, that was one of the big things. Random access to the code. I want to be able to do region of interest, lossless and lossy compression, large images. JPEG was limited to 64 by 64. Single decompressor for multiple modes. JPEG 2000 had 44 modes. Most of them were not compatible with each other. And in the commercial world, they only adopted 2 or 3 of them. So out of all the 44 modes, there's only a couple that really adopted. And then other image types, compound images, topographic images, eye level, right? So they wanted to do more. And then there was a bunch of other requirements that people put in that really weren't going to happen, but they put them in. We want to be backwards compatible with JPEG. They want to be interactive with MPEG, right? So those weren't going to happen, right? But we put it in there just to say, hey, here's our goals. Try to do everything. And so I was working at Kodak Government Division. We did a lot of visual testing of things. And so we took the lead on the testing and evaluation of the inputs, right? So put out a request for inputs. We made a CD of test images of all different types, 30 different types of images. We sent them out to the companies with a questionnaire. Sent them out to 30 companies. I think we got like 12 or 14 back. I think out of that, 8 were complete and several had part. So we did that, and we printed out high quality prints of every single input, every single image. And we had a meeting in Sydney, Australia, started on Sunday, 10 plus hours a day. We were putting out pictures, and people would say, rank them best to worst. And I had a little barcode reader and connected in and put it in the database and sent it off to, it was a 12-hour difference, sent it back to Kodak. Staff people would work on it, send it back to me. And we spent all days doing that. I think the funniest thing there was that many images I put in a carry-on. And so I had a carry-on full of silver halide prints. It had to be 50 pounds. And we put it in the overhead bin and get 2 of them. Yeah. And the guy I was with tried to put it in, missed, fell down, missed the guy's head, but that much, and almost killed him. But we brought them all to Sydney, Australia, did this, right? And we work every day, and then report out at the end of the meeting. And now everybody was there at the meeting to present what they did. And then we presented, okay, here's the results. And we gave them not only the RMS errors, but then the visual evaluations. Out of that, wavelet TCQ algorithm was the overall winner. Now, that has very little to do with JPEG 2000 as a result, but that was the input at the time. And then we started into, okay, now that we have kind of a baseline, now we do more competitive stages where more people brought in algorithms and says mine's better. So we continue to evaluate new algorithms and stuff like that. And so there was about a year and a half of competitiveness where we were really doing, when Majid was leading that organization, subcommittee. And then once we had hey, this is kind of the baseline here, when we went into the collaborative stage where we say, okay, this is the baseline. What things can we tweak? What things can we improve upon? Who has ideas to combine things or something like that? And then we start going into the document stage, right? So when we started in 1994, 95 timeframe, we had about 20 people going to JPEG. Because JPEG, original JPEG was on the decline. It was done. They were doing some, other parts to it that most people didn't use. And so there's only 20 people going to the meetings at the time, 20, 30 people. By the time we were at the height of JPEG 2000 for 2-3 years, we had about 120 engineers from 30 some countries participating in these meetings. Majid?
Thank you, Bernie. Good evening, everyone. My name is Majid Rabanni, and I worked for Kodak for 33 years, the research labs. And for the past decade, I've been a professor of practice in the electrical engineering department of RIT. At the time, I was representing Kodak both at the JPEG and the MPEG committees. Bernie mentioned 94, 95 timeframe. It's noteworthy to consider that the Mosaic web browser, early days of internet, was introduced in 1993. So around that time, the idea of being able to do progressive transmission over the internet, these ideas were just jelly at the time. And I'm going to show you the requirements of or some of the features of JPEG 2000. So JPEG 2000, Bernie talked about the collaborative phase and the competitive phase. The first phase of any standard development is the competitive phase. And everyone comes with their submissions. There were 20 submissions that were evaluated in November of 1997. And these submissions were by all of the heavyweights in the area of image compression, signal processing, from universities, from industry. And I was chairing the coding efficiency group that essentially evaluated from the technical standpoint the merits of these submissions. And the coding efficiency group, which I chaired from 97 to 2000, as Bernie said, as the overall JPEG 2000 grew, the coding efficiency group also grew to about 50 scientists, representing, again, a very diverse parts of industry. And I don't know if we need to do anything about these chats, Wayne, but we've got 16 of them so far, and they keep coming.
They come and go without my control.
Okay, exactly. So we're just ignoring the chats. Okay. So essentially, we talked about JPEG, or Bernie did. The problem with JPEG is that what we refer to as JPEG is really JPEG baseline. And JPEG baseline is very limited in what it can do. JPEG does have extensions. The problem with these extensions is that they either are IPR kind of protected, or they sacrifice some kind of efficiency, and they are extensions anyway. So if they're a new standard, we wanted a single standard that in a single bit stream will encapsulate things like multiple resolutions, multiple quality, multiple visual fidelity, different target sizes for different applications, would go all the way to lossless. If you were interested in some region of the image, what we call an ROI, or region of interest, or also random access to parts of the image. And there are also features that are not in here, such as error resilience, which was very important in mobile kind of applications, which at the time didn't exist, but they became more and more important. So this animation kind of shows that you could access the same image in terms of multiple, again, resolutions, quality, even do a this is the region of interest example, or even access the luminance component, for example, if you're not interested in the color. Now, I'm going to take a quick diversion here and show you a review paper. So I'm going to show you a PDF for a moment. And this is a paper that myself and my colleague, Rajan Joshi, who is now with Samsung, wrote back in 2009. It actually, there was a special issue of the Signal Processing magazine. It's a European magazine. It's called Signal Processing Image Communications. This is January of 2002. And this was a special edition that was dedicated to JPEG 2000. So if anyone is interested in that, you could delve into much more detail on all aspects of the technical aspects, file format aspects of JPEG 2000. This paper, essentially, if I look at all of my publications, the citations of this paper will exceed all of the other papers that I've ever written alone. So that kind of tells you how much JPEG 2000 was really paid attention to at the time. It's about 46 pages, and it goes through all aspects of the JPEG 2000 standard development. So if a picture is worth 1,000 words, in the next 30 or so slides, I'm going to convey to you about 30,000 words, because most of my presentation is just really a bunch of images. Because I want to show you some of these features in terms of progressive resolution, progressive quality, region of interest, and all that, but just showing you some pictures, which come from that paper that I just flashed. So here are the 30 or so images that I'm going to show you. This is just to show that at a very high compression ratio of 128:1, if you use, this is a very high resolution image, 4K by 4K. If you use a DCT-based kind of algorithm, which is what JPEG baseline was based on, these are like 8 by 8 blocks that you probably see as little dots, but you would see what we call blocking artifacts. And at the same compression ratio, that is 128:1, JPEG 2000, which is wavelet based, will create a much more visually pleasing image because all of those blocking artifacts go away. Now, the progressive nature of JPEG 2000 is represented here. And remember, the beauty of JPEG 2000 is that all of these features can be accessed within a single bit stream. Okay, so you have one compressed file, and then you can extract all of these from that same compressed file. This is 1/8 resolution. This is a quarter resolution. This is half resolution. This is a full resolution. This is a small image. This is only 768 by 512, and is not one of the test images, unlike the previous one that I showed, that were used in JPEG 2000. But still, this is something that we used in our paper. Now, the same image now, instead of showing it in progressive resolution, we are showing it in progressive quality. So this is equivalent of 64:1 compression, and then the quality of the image improves at the same resolution. Again, all of this can be extracted from the same compressed bit stream, 16:1. And, from this point on, probably depending on where you are within, how distant you are from the screen, you probably don't see much of a visual loss. But at 1 bit per pixel, you could go all the way to lossless if you wanted to, which will be 8 bits per pixel for that. This is showing you the region of interest kind of feature of JPEG 2000. The entire image as a whole is 1/4 of a bit per pixel, which is about 32:1 compression. However, if you look at the region of interest, you see that this has about 3 times the bit rate of the overall image, whereas the background has about 40% of the overall bit rate of the image. So you could kind of allocate the bit rate to the different parts of the image based on your interest. This is to just show you that you could decompress the image kind of locally. Okay. Now, there are 2 provisions within JPEG 2000 to do that. One allows for just tiling the image to begin with into smaller tiles. Tile can be the whole image, or it could be, much smaller. But even within the tiles, you can access what they call precincts. This is not a tiled image. This is actually, the image is a single tile, but we have accessed about 4 out of the 6 precincts of that image. Now, in order for JPEG 2000 committee to achieve its technical goal, we had to go and modify all of the building blocks, the basic building blocks of the compression algorithm. For JPEG, the transformation part was DCT, block-based DCT, as Bernie mentioned. That had to be changed to what is known as the discrete wavelet transform, or DWT. The quantization, which I will talk about next, had to be redone as well, because we wanted to be able to progressively send the quantized coefficient so that we can reconstruct progressively in quality. And finally, the old Huffman coder, most people have probably heard of that term, of JPEG had to be replaced with a much more sophisticated technology called the adaptive binary arithmetic coder. So all three technologies during the collaborative phase were improved through what we call core experiments. And literally 5,000 or so core experiments were performed in a course of a 3-year period in order to fine tune the technology that finally went into JPEG 2000. So this is kind of focusing on the transformation part. As I said, instead of using 8x8 blocks like the DCT was doing, here the discrete wavelet transform is what we call a full frame transform. You take that image, and in the first stage of the wavelet transformation, you break it down into 4 components. And these 3 are pretty much decorrelated, so they're ready to be quantized and coded. This one is still correlated, so you apply the same transformation only to the top left part and create another set of 4 out of the one on the top left part components, and then we keep doing this for as many times as it takes. So this is a small image, like 512 by 512. So 3 levels of decomposition will get you to a very tiny image, and you'll probably be happy with that. But if you had an image which was 20K by 20K, you could potentially do this 6 or 7 times, each time getting a resolution that would be 1/2 the resolution of the previous seed. And then each of these components, they're called wavelet coefficients, and they will be, it's very quite, involved. So I won't really be able to get into the details of how that was done, but at least in the basic decomposition is the wavelet decomposition. Now, there are 2 choices of wavelets. One is very efficient, but it's floating point, so a little more complex. One is integer-based for lossless applications. So, the implementers could choose any of those 2 choices. The other aspect that had to be addressed was, how do we create a quantization that would allow us to progressively improve the quality of the reconstructed wavelet coefficient? You saw those wavelet coefficients, they get quantized, and now we have to send them to the decoder. Well, we want to send them in a way that the decoder can decide to decode up to a certain point and reach some level of quality. So the way that it works is that if you could visualize that wavelet decomposition that we had, this was that kind of top left image, if you will, and these were the other wavelets, bands. And then when we quantize it, the quantizer, we are showing here, like 1, 2, 3, 4, 5 levels, or 4 levels, but it could be 12, 16, depending on the bit depth of your image. There are all these representations, what we call bit planes. So imagine you quantize at up to lossless, if you will, or you can quantize that wavelet coefficient with very high accuracy. But if you just take that quantized index and represent it as a binary number, and just send the most significant bit plane of that binary number, you will have a very coarse kind of reconstruction of that index. Then you can refine that by sending yet another bit plane and another bit plane and another bit plane. Now, I make it sound easy because the actual coding of these binary values is quite sophisticated and cannot be done with Huffman coders. That's why we had to go to the adaptive arithmetic coder. But the basic idea of being able to represent a quantized coefficient with bit planes and then refine that is pretty straightforward. So here I have an example of an actual floating point coefficient value, which is minus 19.38. Okay, and the first 3 bit planes are just zeros. Okay, let's see how accurate can we get. This is the actual value that we want to reconstruct. After sending 3 bit planes, our reconstruction is still at 0. Okay, so we really haven't learned much other than if we were to reconstruct this particular quantized value, it'll be 0. But now look that as the next index, we have sent 3 zeros now, we send a 1, The reconstruction is still coarse, but instead of minus 19.38, it's minus 24. And now we have like some quantizer bins. It's not just a single bin. And as you see, progressively, it just gets more and more refined. So now it's reconstructing at minus 20. You could kind of follow this and see how close it gets to that. The other thing to look for is the width of these quantizer bins. They could go all the way to lossless if you wanted to. And you see that this requires what we call an embedded quantization scheme. So that was another kind of refinement that was done to, and you can just keep doing that. Okay? So now you have very fine quantization, and you are within this bin very close to the true value. And if you keep sending those bit planes, then eventually, as I said, if you choose the lossless option, you can send it losslessly. Now, the challenge would be, of course, how are you going to encode these zeros? Because when you're doing a bit plane, it's either a 0 or a 1. And if you were to send a 0 as a 0 and the 1 as a 1, then you haven't really compressed anything, right? So you need to somehow extract all that information from that binary decision and compress it in a way that will give you the compression ratios that JPEG 2000 does. So the technology here was called the adaptive binary arithmetic coder. Okay? And this is in contrast to the Huffman coder of JPEG. The arithmetic coder has quite a history. Okay? IBM developed it, called Q coder. Then Mitsubishi had what they call the MEL coder, and AT&T had also their M coder, if you will. And they all got together and they created a combination, because everyone wanted some IPR right in there. They created a combination that was called the QM coder. The QM coder went into JPEG, original JPEG extension, also went into JBIG. The problem with the QM coder was that it was IPR protected. And one of the main issues, and I think Rob will also talk to this, was of JPEG 2000 was that we wanted royalty-free JPEG 2000. So we were not able to use the QM coder. The QM coder is very efficient, very good, but I'm sorry, the MQ coder, it's kind of sometimes confusing. The MQ coder is very efficient, but then there was another version of that everybody agreed upon called the QM coder, and that went into JPEG 2 and also went into the JPEG 2000, and it's royalty free. It's only about 0.5% less efficient than the other coder. And I'm going to end with a few images. Okay, you wonder what that is. You will soon see. But this is, I have about 11 bit planes on this image. Okay, I showed you the quantizer refinement. This is the highest level bit plane. Okay, if you actually look at we call it bit plane 1. This is the most significant one. If you look at the actual compression ratio, that's written here, 12,483 to 1. Okay? It's really impressive, but of course, you almost get nothing for that amount of compression. Now, things to look at is how this number gets smaller and how this image gets more and more clear. So this is after you send the second bit plane. This is after you send the third bit plane. The compression ratio here is still about 1,500 to 1. This is after you send the fourth bit plane, still about 600 to 1. This is after you send the fifth one, the sixth one, the seventh one. You're still about 50 to 1 compression here. And you could go all the way to lossless, right? But at some point you might say, well, I really can't see visually any difference between the compressed version and the original, depending on what application you have, target file size, whatever you can stop. This goes all the way to even the next bit plane level. And of course, you probably won't be able to see any visual difference between the last 3 or 4 images. And I think with this, I'm going to hand things to Rob. I don't know if you want this pointer or not, or you can have it.
Thank you, Majid.
It actually is from Xerox.
Hi, everyone. I'm Buckley. I was on the format sub-team The head of the team was Scott Houchin, who was also with Kodak. Now, the next thing to do is to take the code stream that Majid described and package it with the metadata to deliver it for particular applications. Now, one of the proposals was to use TIFF, which had been around for a while, it's a well-known format, and it had a free library. The problem was, though, that some of the stuff we needed, like XML metadata and ICC profiles, was not part of the TIFF spec at the time, so we'd have to extend it. So the idea was to start with something newer. And we used the Apple QuickTime format, which consists of atoms, or what we call boxes. So you take this one little segment, it has an ID, it has a length, and it has the data. And so the formats that JPEG 2000 uses are all based on this idea. Now, this is the format defined in part 1 of the standard, the core format, JP2 files, we call them. The very first box tells you it's a format in the JPEG 2000 family. The second box tells you which one. Now, the different part, the JPEG 2000 standard has several parts looking to design for different applications. So parts 1, 2, 3, 6, and 15 all define their own formats. The file type tells you which one it is. Now, in the case of JP2, you have a header box which has the technical metadata. You've got the compressed data, you decompress it, but you need to find out, well, what's the resolution and what color encoding does it have? That's where the technical metadata comes in. What we did originally when the standard came out is we had 2 color encodings, sRGB. Remember, this was 1999, 2000, and the ICC input profiles. I'll come back to that in a moment. We have the CodeStream box, of course, with the CodeStream that Majid described. Then metadata boxes is one or more. You have XML encoded metadata, and if it's not XML encoded, you have UUID, Universally Unique Identifiers. Fine. So very simple structure. I said there are several different formats defined within the spec. Bernie mentioned that one of the requirements was to handle compound documents that consist of images, text, and graphics. That was the part that I worked on. That was part 6 of the standard. So it defined its own format called JPM, which used something called mixed raster content technology from Xerox that enabled you to combine JPEG 2000 with other encodings to meet the needs of those different content types. That's another story, but where we're at now is, so we have part 1 has been done, or just about to be done. And now comes the part of who's going to use it, how we're going to use it. So now we want to talk about the adoption. So I think with that, I'm going to turn it back to Bernie.
Yeah, so I think there was a couple of things that made JPEG 2000 successful in its market, right? One of which is the compression efficiency was better than JPEG, right? And at the time, that was still really important, right? The functionality, as we talked about, as Majid talked about, was critical. But from my standpoint, there's a couple of things. One of which is all the people that are in there, we were working with other standard organizations, and those standard organizations adopted, right? So DICOM, which was medical imagery, right? OGC, NATO, NGA was geospatial. And then another one was digital cinema, right? Which didn't even exist when we started this. Digital Cinema Initiative adopted it. And they all made their own profiles of JPEG 2000. So it made recommendations on how we want to make our standard encoding, right? And then the other thing was Kakadu software. David Taubman and Dr. Marcelin were writing the book on JPEG 2000. They got together, they're writing the book. And David Taubman, besides being brilliant, was prolific, right? He wrote things quickly. He did things very quickly. So he wrote his half of the book while Dr. Marcelin was writing his half of the book and handed to, because they were going to switch back and forth. And David was done so quickly, he was kind of bored. So he goes, you know, what would be really cool is let's write some software and have example software in the book, right? So every book came with a CD of Kakadu software, right? At the time, I was working for Kodak, and we were writing our own software at JPEG 2000, and I had spent on that project probably $60,000, $70,000 already. Two software people, a couple months, right? We had gotten to a certain level. This Kakadu software came out, and it was faster, better, more complete than anything that we had done. And we went to him like, well, can we buy a license of this? He said, yeah, $5,000. You can have the source code. You can take it up. I'm like, thank you very much. And I fired our software people and, not really, but, so then we started taking that software and modifying it to our needs. That right there, I think having that software, which was kind of the baseline of most everybody's version of JPEG 2000 was critical. And then also IP free, right? The reason Digital Cinema bought into this was because they didn't have to, have streaming, rights and stuff like that. Other issues, why it didn't get adopted further was the computation complexity. It was significantly more computationally complex than JPEG originally. So when you think about digital cameras and cell phones, right, they all use JPEG or some version of that now. They would never use JPEG 2000. With that, because of the complexity, there was very limited hardware and fast software. And the consumer market didn't really adopt it, right? Nowadays, storage and transmission is significantly cheaper, so the 10% or 20% or even 30% compression efficiency that was critical back when this happened is no longer that important, so it's not being adopted for other consumer applications. I will tell you some of our successes when I was working at Kodak. Up until when I was working for Celis and L3 Harris and doing a lot of government work. Back in the day, Kodak had a project called CityPix, where we had 84 cities that were high resolution digitized aerial photography. Back before Digital Globe, or back before Google Earth and things like that, right? This is, Kodak had some great ideas. It's what Google Earth ended up really doing, right? But we had all of these images. We were getting rid of the business. We sold it to Global Explorer, which was, going to be a competitor to Google Earth, or, was prior to Google Earth. And they didn't know how to do anything with it. So we actually took the new software, made an internet browser application where we took all the data, took the resolution and regional dimensions that you were interested in, and converted it back to a JPEG file that would be splashed on the screen in real time. They loved this. They thought that was the greatest thing, which then turned into, we made libraries for NGA that would take in all of the commercial imagery that was being collected at some point, 70 terabytes a day, with all of the commercial remote sensing systems that were actually built. The cameras were built at Kodak for all of these. So back in 95, 96, when we started this, we were starting to build the first Iconos satellites. And then more recently, Gorgon Aster, which I worked on, which was that system that collected 1 billion pixels, 2 frames per second. We made hardware that compressed that in real time and then streams region of interest to anybody that wanted some on the ground, right? And so there's been some really great successes with JPEG 2000, even though a lot of people don't really know, it's not in consumer cameras, it's not in a lot of other things. Digital cinema. This was one that we didn't even know about when we started JPEG 2000, but that is basically, digital cinema started like 1999, first kind of demo. The real pusher here was they wanted to reduce their costs, right? Every film that you make copies of cost about $1,500. You had to ship that everywhere. There was 2 main things on the positive side was just it was cheaper, right? Just a hard drive versus a roll, multiple rolls of film. The other thing was, if the movie was a flop, because it was so expensive to put these things out, they would, release in Europe, then America, then Asia, or wherever the movie was going to do best. So if the movie was a flop, then everyone knew by the time they went to the right. So digitally, you could do it instantaneously, everything, right? And so even if it was a flop, you still get that big first weekend. Not that there was an alternative, right? But the first J2K was Serenity in 2005, and then the first one distributed was Inside Man with only 20 theaters in 2006. Now, whenever you go to cinema, JPEG 2000 is the base, right? And so part of that is the resolution. Some of the theaters are 2K, some of the theaters are 4K. Now they're getting an 8K, right? So the ability to do that, they still send hard drives, but they do have some internet versions and some satellite connections to do that too. That's rough.
By the time we're done, you may think like we do that JPEG 2000 is the most widely used format that no one's ever heard of. This is a picture I got from a colleague of mine named Pierre-Anthony Lemieux. He was at the International Broadcasting Convention earlier this year. And here's a machine that scans film. And what it's up, it says JPEG 2000. What it does, it has one JP2 file for each frame, combines it with the audio, puts it in a container format called XMF. So a lot of this going on. The next slide I want to show you, this is from Harvard Library's Digital Repository Service. This is also their 25th anniversary year. This is the first JP2 file they put in their repository. And this was the week before JPEG 2000 became a standard. They tell me this is a picture of an item from a Chinese ethnographic collection from the 1930s. So that was really the start of JPEG 2000 and the documentary heritage environment, which I'm going to describe to you. So it started in 2000. I told you that what we'd done is, in the original, is we put in sRGB and in ICC input profile support. Well, it turns out that people who were capturing images were using RGB display profiles, not input profiles. So we had to amend the standard to fix that, so they had something they could use for their data. 2004 was also the inaugural IS&T archiving conference. At it, there was a short course on JPEG 2000. I taught that. And there were 4 papers on JPEG 2000, including one to describe the Aware image server, which is making available the academic papers of a man named Charles Olson on the Herman Melville project. So that was probably the start of using JPEG 2000 to provide access to documentary heritage and cultural heritage. At the same time, University of Connecticut that year had a symposium on JPEG 2000 in archives and libraries. So they're already moving towards that area. I also mentioned NDNP. That was the U.S. National Digital Newspaper Program. The idea there was to make available on the internet a searchable database of historical U.S. newspapers. 2 years later, they came up with their technical guidelines. It included a JPEG 2000 profile that Xerox authored for them. And a year later, the site was launched. So all this is beginning to happen. The next major events were in 2010. An organization in the UK called the Digital Preservation Coalition had a practitioners meeting where they brought together, mostly from Europe, people to talk about their use of and plans to use JPEG 2000. Just before that, I had put together a technical report for them, came out in 2008, that has the title JPEG 2000, A Great Step Forward for Archiving Community, which I thought was a rather formidable title, quite ambitious. The other thing that happened in 2010 is FAGI's first edition came out. How many people have heard of FAGI, the Federal Agency's Digitization Guidelines Initiative? That's what it's called then. Now it's the Federal Agency's Digital Guidelines Initiative. It was led by the Library of Congress. The idea was to bring together U.S. government agencies who had to do digitization and establish some common practices so that you would have a common baseline for quality and also consistent outputs no matter where the material was scanned and digitized, whether it was internally or you sent it to an external vendor. Their very first edition didn't mention JPEG 2000, but they were kind of non-committal about it. At that time, TIFF was still the preferred production master file format. 2011, the Library of Congress had a summit where they brought together a lot of people to talk about JPEG 2000. Some people who were already using it and some people who were thinking about using it. Now, the other thing that happened in 2016, FAGI came out with their second edition and things had changed. They now had JPEG 2000 as an acceptable master format, but they still preferred lossless, not lossy compression, although they admit you could use lossy, but their recommendation was to use lossless. The next milestone I want to point to is part 15 of the JPEG 2000 standard came out in 2019. HTJ2K, high throughput JPEG 2000. Now, Majid told you about the three stages in the JPEG algorithm: the transform, the quantizer, and the coder. The JPEG 2000 coder, the arithmetic coder, was the best from the tests that were done. It was also really slow. So what this part did is they replaced that coder with a block coder that was a lot faster. That was a big plus. It was also easier to implement in hardware. On the downside, though, is that it wasn't as coding efficiency wasn't as high, and you lost the ability to do quality scaling. But it's considered that the speed was a big advantage. That brings us to 2023. That was a FADGI third edition, and things really had changed by then. I mentioned already that JPEG 2000 had already appeared in the second edition. In the third edition, it was still there. But what had really changed is now they were recommending that you consider lossy JPEG 2000 compression. So we've gone in the span of just 13 years from recommending or preferring uncompressed TIFF files to recommending that you consider using lossy JPEG 2000. At the same time, of course, you could use TIFF if you're scanning material for the government agencies. You could consider using TIFF, PDF, PNG, or JPEG 2000. The other thing I want to point out to you about 2023, and this has to do with the U.S. National Archives and Records Administration. They put out a regulation. It was part of the move towards an all digital government, so that when you submitted the records to the archive, they wanted them in digital form. They were no longer going to be taking paper. What that meant was that if you had a paper record, you would scan it, discard it, and in its place send a digital file to the National Archives for long-term, for them to keep long-term. You can read all the details here. The point I wanted to make, though, is that when you look at this table of what they will accept, the formats they'll accept, there's two things to notice. Of course, TIFF is JPEG 2000 is on the list, but the other file formats are TIFF 6.0, PNG, and PDF. Those are all older file formats than JPEG 2000, believe it or not. They all were preceded in the 1990s. Now, to be fair, PDF came out in 1992. PFA was a restricted subset that was done in 2005, and PDF didn't add JPEG 2000 support until 2011. But JPEG 2000 basically is the most recent, most modern of the formats that they're now accepting. The second thing I want to point out is that they also are allowing lossy compression. Now, that's a major thing because for a long time, this committee was very concerned about the files they scanned, that they wanted to preserve the scan. Don't mess with my scan. Now they're recognizing the scan. There's nothing special about the scan at all. And this gives you a lot of opportunity to have a lot more file savings and storage savings. I want to show you an example of what that is with this image. This was a test image from the Wellcome Library. It's actually a painting of when John Milton met Galileo in the 1600s. It's a meeting that actually happened. Now, whether this image is, I show to you, uncompressed, 10:1 compressed, whatever, at this scale, you can't tell the difference. So let me zoom in on a particular area. If I expand this, even on for the pixelation, this is the uncompressed portion of that image. Now, what I'm going to show you is a losslessly compressed, sorry, let me put it again, a minimally lossy compressed image. I don't know, can you see much difference? As I go back and forth. What minimally lossy means, if you go back to the block diagram that Majid showed you, I do the transformation and the quantization, but I keep all the data and I code it. I don't discard anything at all. So I keep all the quantization levels. When you do that, how much you compress the image depends on the picture and the image. It can be, in my experience, from 4:1 to 8:1. Now, if I go a little bit further and I start discarding data, I can actually discard enough to get down to 10:1 compression. And most applications operate at this level. If they do, discard data. So now if I flip back and forth, you can see more difference now, right? Can people see the difference? Yeah. But again, when at most uses, it doesn't make a difference. There's nothing special about the scan. The other thing that was really interesting is that when Fawzi came with the second edition, they introduced a rating system for image capture. You could be 1, 2, 3, or 4 star. 4 star is the best. For most government applications, they require 3 star. Now, it turns out if I take an image and I JPEG 2000 compress it, say minimally lossy, it still meets the spec. So compression is like free. Doesn't cost you any quality at all. Now, the interest in the documentary heritage community with formats like JPEG 2000 is twofold. One is an archival format, and second is an access format. And with JPEG 2000, they can do both. Now, you have a lot of programs already existing that offer things like newspapers. The U.S. National Digital Newspaper Program that I mentioned earlier, the British Newspaper Archive, Sweden, Norway, Netherlands all have newspaper archives. There are a ton of places out there that are offering access to stored materials. Family Search. Are people familiar with Family Search? It's part of the Church of Jesus Christ of Latter-day Saints. When I talked to them back in the mid-10s, they were creating 300 million JPEG 2000 images a year. I haven't gone back to check, but that was their format. I want to show you this because this was a project I was involved in recently. The Arabian Gulf Digital Archive. It was a joint project between the National Army Archives of the UAE and the National Archives of the UK. A lot of the records for that part of the world, they call it the Arabian Gulf, the British called it the Persian Gulf, are in the UK National Archives. And this makes them available online for scholars and people interested. Citizen archivists, they call them. So let me look at I want to show you one particular set of files. There were a series of treaties that the British had with the tribes and sheikdoms along that part of the coast of the Arabian Peninsula from 1820 to 1971. So what I'm going to show you is what you get to see in just all of these different kinds of systems. You can scroll around, zoom and pan. Nothing special about this. Everybody could do this. What they don't tell you is underneath all of this is JPEG 2000. This particular site is supported right now. They're still adding images to it by a million JPEG 2000 images. You don't know that. You don't see it. You can't download them as JPEG 2000. But this is what's supporting the zoom and pan that you see here. So you can scroll around. You can see how they sign treaties with people like in a place called Dubai, which you probably now know is Dubai. You can pick other pages. This was the English. This is the Arabic, the other treaty. This was the original treaty in 1820 that they used to end the hostilities between the tribes and sheikdoms along that part of the coast and the British. And all the people who agreed to the treaty with them would fly this particular flag. And this was the start of a truce between the British and these tribes. As a result, these were known as the trucial states. I don't know if people have heard of those. Anyway, these treaties lasted till 1971, when some of the trucial states came together to form what we now know as the United Arab Emirates. So a little bit of history, but like many of these systems, many of these programs, underlying it all is JPEG 2000. When you want to download these pages, what you download is a PDF. So The fact that your browser does not support JPEG 2000 doesn't matter. Bernie told you how the committee may have boxed itself in when it decided to call this JPEG 2000. I'll finish with one last story. We were meeting in July 2000 in France. One more meeting that year in December. Now, the way a standard works, the way it progresses, you have a proposal, a new work item that goes to a working draft and a committee draft, to a draft international standard, to a final draft international standard, then an international standard. It progresses through these after a period of review with a vote at each meeting. The trouble is, that summer, we are 2 stages away from the final standard with only 1 meeting left. So it didn't look like we'd finish in 2000. So what to do? The solution, and I'll credit the U.S. delegation that Bernie headed with this, that Bernie headed at the time, invited the JPEG committee to a meeting in Rochester in August 2000. So it was sponsored by Kodak and Xerox. That was the fourth meeting that year, but the second meeting. So we had 2 meetings after that. So we were able to finish JPEG 2000 that year, approve it at the meeting in December. That's when it became an international standard, which is why we're here today. Otherwise, we would be celebrating JPEG 2001. But anyway, that's my part of the talk. If you have any questions for any of us, we'd be happy to answer them. Roger. Yeah.
So Rob, the task that we do is, collect a bunch of 16-bit, 16-bit images and then go and construct derivatives of them. And oftentimes many derivatives. Is there any value to consider storing those 30 as JPEG 2000 instead of TIFF, which is what we're doing now, and then decompressing them and then processing to get the derivatives from the decompressed ones? Because, you can go down to Mike Karen's been down at my lab, there's disk drives everywhere.
Yeah. Well, that's what a lot of people did. I don't know about your particular situation, but what a lot of people did is they used a JPEG 2000 file as the access master for creating derivatives. Now, JP2 might not work for your application, but there are other formats in the family that might. Like Part 2 defines one that can handle many more components, and I believe is being used for spectral. But most of the people I talk to, most of the work I do, the JP2 is just fine.
Yeah, there is the Part 2, they did a spectral version. So if you had hyperspectral data or something like that, you could put them in multiple bands, or you can actually try to decorrelate those bands by using another spectral label.
Different sense of master's thesis.
Yes.
Okay, Roger, you forgot to ask the most important question. Where are your Oscars?
That is the committee has won multiple Emmys for different things. The Oscar, we were denied because the Oscar committee only gives technical Oscars for things that are designed and specific for the film industry. So if it's not specifically for them, we tried to do, we made a profile for the film industry, and it just didn't fly.
And it was all free.
I know. There should be something there, because the amount of money that we've saved the film industry was significant enough that, and if you go to a theater today, right, and specifically when you start thinking about 3D movies, right, you don't have 2 film trying to jitter and connect anymore, right? It's all digital. So, that is a huge advantage from where they were, right?
So,
Sit around.
yeah. So, a more serious question. Knowing what you guys know now, is there anything that you would have done differently that you might have tried to improve on?
I truthfully think that the high throughput JPEG 2000 is probably a better decision because of the computation complexity of the arithmetic encoder and the bit plane encoding. Because the quality scalability wasn't that useful as much as the resolution scalability for the larger images, and maybe other applications thought it was good, but in general, I thought that the region of interest access and the resolution scalability was the most critical. But so I think some of the computation complexity helped JPEG to this, man.
Okay, so basically, well, sort of a corollary to that question is that you always have that the old Betamax versus VHS VHS competition doesn't always mean that the better technology wins.
Right.
What? So are you saying that that's probably what the better technology that you would have wanted to have?
So I think that the bitplane encoder gave us the functionality, gave us better coding efficiency, right? But that came at a cost that was too much for what it gave, right? If you did something different, it could have been more, I think, more successful. Could have hit the consumer market more. But
Okay.
and again,
Yeah, no, that's
hindsight.
we all know from history that sometimes whoever adopts something not necessarily for technical reasons actually is the market. So
This is the slide we didn't go over. What JPEG committee has done since JPEG 2000. And as Bernie said, probably the most interesting thing as far as we're concerned on that list is the JPEG 2000 Part 15, the high throughput. So,
A lot of these, JPEG XR was Microsoft and pushing their kind of technology and it wasn't successful, right? So there's a lot of standards out there that are not successful, right? And we're following with the original JPEG standard, which Majid was part of. It was very hard to follow because it was the most successful standard.
we're not in the room anymore. So, like you, we read about these standards. XS, for example, we received a technical Emmy last month for its use in video transport. But it uses a wavelet. It focused on hardware implementation, so it's very low latency, low complexity. But it has, it's not free IP. There's a license pool, so you have to pay for it. XL, it uses block transforms like JPEG, but variable size, so it's much more sophisticated. I think Apple's using it, Microsoft's now using it, and just this week, the PDF Association said they're going to use it they're going to add it to PDF. But it's really aimed at the camera and the web market, not quite the same market served by JPEG 2000. JPEG XI just came out this year, so it's really too soon to say much about it. And XC, I'm not even going to talk about that. They haven't even got the requirements out yet. So, but it's mainly meant for computer vision applications.
is that a typo? AI.
No.
Also,
There is a JPEG I standard.
statement as to what that's all.
Again, not in the room, so I don't know.
It just came out. It's got training. It's got a neural net. It's hard to say where it's going.
The implications of because one of the things that people are thinking about AI is that we need to limit the paradigm to something visual for certain tasks.
Yeah.
And the question is, what is that?
Yeah.
I mean, so far what I've heard is, the AI may decide to, that's not important, just get rid of parts of the image, right? So there's issues there, right? But it's the AI moves quickly.
But in the last few years, there has been an effort within the scientific community to apply neural networks to the transformation part, maybe the quantization part of compression in general. And, there's been work going on in industry, in some universities. And I think JPEG AI is probably an effort to kind of consolidate that effort and see if there is really a standard that could be established around that. But this is very, very preliminary.
Yeah, things move so fast in that domain that I can't even imagine how a committee would standardize.
Yeah, I mean,
everything.
if you think about like, JPEG, right?
Yeah.
JPEG was based on technology that was developed 30 years before that, right? JPEG 2000, 10 years or 15 years before, right? To do something in AI right now, it's moving so quickly that by the time you standardize something, right, it's hard.
Well, that's other than we talked about the future because I showed you that slide on what the U.S. National Archives did in 2023. And they basically said, okay, we're going to go full in, among other things, on JPEG 2000. And that's like 23 years afterwards. And if you don't like to use JPEG 2000, you can use TIFF 6.0, which is even older. So, but they're mostly concerned about something that is reliable and sustainable, and they can count on being around. So
Was there any crossover between the committee, the TIF committee, or at all? Was there anybody that you were able to talk to? Or
I didn't know that I didn't know there was I didn't know there was a TIFF committee. Adobe, by that time, Adobe owned TIFF.
Adobe was part of the committee, so they had people there.
I don't think TIF was ever standard.
Adobe some standard.
No, Adobe did a rental copy, but I don't think it ever became an ISO standard.
No, but there were, but David, there were there's TIFF EP, there was TIFF FX, there were different industries, different like IDR.
That's right, but they were industry and or Adobe supported Redbook kinds of things.
Yeah.
Because in the graphic arts, we try to use TIFF. And the real problem we ran into, and I don't know whether any of your other things ran into this or not, but we created some ANSI standards for TIFF, for an application of TIFF. And we had to extend TIFF, which meant that none of the standard TIFF processors could handle the specialized TIFF that the graphic arts used. And that only lasted for a very short period of time. We gave up on using TIFF because the problem of both extending and restricting a standard became very complex. The reason we were successful with PDF was we worked with Adobe and we made an agreement with Adobe that we would not, in any of our standardized versions of PDF, and there are several, we would not restrict, we would not extend PDF. We would only restrict the Redbook version of PDF. And Adobe agreed to work with us. And where we hit a hard spot and needed more capacity, more capability, Adobe agreed that they would go back and revise the original standard with our original Redbook with our help, so that that would maintain compatibility. And in fact, they came to the graphic arts later on and to the document committee. And that's when PDF itself became an ISO standard. And much of that, in that final ISO standard, incorporated a lot of the stuff the graphic arts had done to make it usable in the graphic arts.
Other questions?
I got one quick one. So Bernie mentioned that it handled multispectral data. Two questions. With regards to multispectral, multiplanar data, does the compression exploit any correlation between the channels? And the second question is, what are the limits on bit depth?
Bit depth, 38 bits per component, I think, something like that.
Yeah.
At least in TIFF, and at least in JP2.
It was I mean, commonly the word won't pass 16, but it had the capability to go to 30, 38 or something like that.
Oh gosh.
And then the part one does not actually do anything about spectral transforms besides color transforms. So 3 and 4 band, I think, is the limitation. But part two, the extensions, actually allows you to not only use the wavelet filters that they define with the 5397, but you can define your own wavelet filters or other transforms
Yeah.
that go between bands and do that. As a matter of fact, IS&T just 25 years later just adopted JPEG 2000 as part of one of their interframe coders. That's awesome, right? And now statement was to me was now you can have hyperspectral video. I'm like, all right.
Well, thank you very much. One more time.